So let's get to the first law, law of conservation of mass. Okay, so this is a big one right here. So basically, this is in a chemical reaction, matter is neither created nor destroyed. Matter, right, if we remember from last time, matter is basically anything that is going to take up space, right, and has mass. Okay, so this is what matter is. Now understand, right, when we say it cannot be created nor destroyed. So it's not coming out of anywhere, right? It's from something. Okay, so matter isn't just going to disappear if it, just leaves. So that's saying like the energy, I'm looking at Raising Dion, but he said that energy, is saying is the same concept, right? But we're going to get to the energy part of this later on. But right now, we're just focused on the law of conservation of mass. Law of conservation of mass. We have mass of reactants equals to mass of product. Okay, so mass of reactants equal to the mass of product. So, for example, let's say that we got some sodium, right? And this is what sodium looks like. It's just a solid metal. And then we have some chlorine gas. Okay, so we got our sodium and chlorine. And when we combine both of these reactants together, right, we're going to get table salt, sodium chloride. Let's look at specifically, right, how many grams of sodium and how many grams of chlorine we have. Okay, so I have 7.7 grams of sodium and I have 11.9 grams of chlorine gas. Okay, so we have a total mass of 19.6 grams. All right, so this is the total mass of my reactants. Now let's look back to law of conservation of mass. In a chemical reaction, matter is neither created nor destroyed. So when we're talking about this conservation of mass, right? When we go to make our table salt, what do we see here? We have 19.6 grams of sodium chloride, the exact same mass as our reactants. And this is what we need to understand, right? Just because when we make a new product or something new, right, we have to have that same mass, right? That matter is not going to disappear. Okay, it will not disappear, right? So we're going to have the same amount of sodium and chlorine that we put in, right, to this reaction. We're going to get that same amount out of the reaction, which we're going to see here with 19.6. Okay, so this is how we have to think about our conservation of mass. That matter is going to stay constant. That's the key thing, it's constant. All right, so you put in a certain amount, expect to get out a certain amount. So we're looking at another law. Okay, the law of definite proportions. So let's talk about it. All samples of a given compound have the same proportions of their elements. This is the law of definite proportions. So specifically, let's break this down, right? So basically, any sample that you ever have of a compound, right? And if we remember, a compound is two or more elements, right, combined together. So any sample that you have of a compound, right, will have the same proportions of their elements. Okay, so no matter the compound, it's going to have the same proportions. So let's think about this. So let's say I got two samples, right? We got carbon monoxide. Now, in case you don't know exactly what carbon monoxide is, that's just a carbon and an oxygen, right? CO, or if y'all look on the other side, it's like CO. Oh, wait, there we go. Oh, all right, so carbon monoxide, one carbon, one oxygen. Okay, so we're going to have this compound, and it's going to decompose to the elements. Okay, so we got one sample that's going to give me 17.2 grams of oxygen. I don't know why Fetty Wap just 1738. No, okay. So 17.2 grams of oxygen and 12.9 grams of carbon. Okay, so this is the first one, right? And remember, we got a carbon monoxide decomposing to give me oxygen and carbon. The other sample is once again still carbon monoxide, but it's going to decompose to give me 10.5 grams and 7.9 7.8 grams of carbon. So let's show, right, how this is going to be related to the law of definite proportions. Because once again, the law of definite proportions is telling me, right, that compound is going to have the same proportions of their elements, no matter. Okay, all samples. So if I look at the very first one, right, we know that carbon dioxide is being decomposed to carbon and oxygen. Okay, so we're going to see here, right, for my mass of oxygen, I got 17.2. And then for my mass of carbon, I get 12.9. So if I divide these, right, divide these two elements to get a ratio, in this case, the ratio I get is 1.3. And this is my ratio for this carbon monoxide compound. I should always have this amount of oxygen over this amount of carbon. It's always going to be 1.3. It should be, at least. So let's double check. So, right, the next sample I have is 10.5 grams of oxygen and 7.8 grams of carbon. All right. So is this going to give me the same ratio? Right? Correct. It will give me the same ratio. Right? Because the mass of oxygen, right, we're doing the same thing, getting our ratios here. 10.5 divided by 7.88 equals 1.33. The same exact ratio as my other sample here. And this is essentially law of definite proportions, right? All samples, any sample that we ever have of carbon monoxide, if it is ever supposed to decompose to my two elements, it's always going to be this same ratio. Okay? Because if it's not this ratio, right, say I got a 2 here, I don't have carbon monoxide, I have something else. So in order, right, for this to be carbon monoxide, it's going to have to decompose in this manner here. Okay, and this is all what law of definite proportions is. It's telling me, right, the proportions got to be right, got to be the same. All right, so we're still talking about these laws here, and let's cover this last law, the law of multiple proportions. Okay, so before we was talking about definite proportions, now let's talk about multiple proportions. So this law states that when two elements from two different compounds, all right, the ratio of elements in the compounds can be reduced to a small whole number. Okay, and this is law of multiple proportions. No matter what, right, it's always going to be able to be reduced to a small whole number. So let's just look at an example, right? Let's look at an example. The mass of my oxygen, when it combines with 1 gram of carbon, right, we get, for this case, 2.67 grams. All right, this is how much we're going to get when our mass of our oxygen, right, is going to combine with my 1 gram of carbon. For carbon monoxide, right, it's going to be the same thing, the mass of oxygen that will combine with carbon again. But in this case, right, I have less amount of oxygens, in this case 1. So I'm going to see that be 1.33 grams. Okay, so smaller makes sense. I got less oxygen. This one has more oxygens. This is the reason why it's a bigger mass, less mass. Now let's talk about law of multiple proportions, right? So when two elements, in this case our two elements are carbon and oxygen. Those are our two elements. When two elements form two different compounds, so in this case, my two elements are forming two different compounds. Carbon dioxide is one compound, carbon monoxide is the other. Okay? So when they form two different compounds, the ratios of those elements in the compounds can be reduced to a small whole number. So this is telling me, right, if I take the ratio from my carbon dioxide and my carbon monoxide, I should be able to get a small whole number. Well, is that true, Dr. J? Yes, it is. Right? So if I take my 2.67 and if I divide that by 1.33, right, we're going to see here, right, it's going to be reduced to, what do you know, a small whole number. And What's crazy is this is the case for a lot of these different types of elements, right? These compounds. You got two elements forming two different compounds. It will always be reduced to a small whole number, right? And this is the law of multiple proportion.